Okay, we found out what functions were, and then the vertical line test to test whether something's a function. And then we have kind of, well, actually, let me back up. So we've determined whether things were functions by looking at the tables. And then we kind of realized, oh, hey, if the table works like this, then the graph's going to work like this. So then that brings to the vertical line test. That's tables and graphs. And then we kind of explored that idea a little bit more with some graphs. But now we're here and we got to answer a couple things. So one, a linear function is a relation whose equation can be put into this form, y equals mx plus b. Any y equals mx plus b will automatically be a linear function. Now keep in mind that horizontal lines count in that. Horizontal lines are lines that just have an m of 0. Right? So this is totally fine. But what they won't happen is x equals. Right? X equals is no good to us. X equals can't work like this. Right? And therefore it's not going to be a function. So if it's x equals a, we're in trouble. Okay? All right, so that's what a linear function is going to look like. Y equals mx plus b. So we're supposed to determine whether these are functions. And now this is the algebra portion. And I'm going to talk about it in the next page, but I can talk about it a little bit right now. So we have kind of these big ideas. So we have, and this is going to tie into something else about the rule of 4, but let's just keep in mind that when you have a function, or any relation in algebra, to be honest, when you have that, you automatically have the equation part of it, the algebra. That's what algebra is. It's the part that involves the x and the y, the letters. That's algebra. Then you have kind of a table. That's the numerical thing, right? How do the numbers work, right? So if you have a table, that's numerical. Then you have your graph, right, which is kind of self-explanatory. And then you have the words, like function, right? So when you describe something in words, say like terminology, when you're using definitions, that's that. So for this definition of function, we've used these 4 things without even realizing it. And they all are useful for us. And we're going to keep doing that for all sorts of problems. Because in our class, you can define things with algebra, or you can find things numerically, or you can find things with a graph, or you can talk about them in words. Usually the word end is on my side. I mean, I write you problems, and then, with English, that's words, right? And you've got to figure out what the heck I'm talking about. So I usually am the one to write up the words, but not always. Sometimes I'll give you some words and ask you to explain yourself, and that'll be other words, right? And then you have the algebra portion, and then you have the numerical and the graph. So we already did the numerical stuff. That was right here. When we're looking at tables, that's numerical. Then we started looking at graphs. That's the graphical stuff. And now we're here looking at just the equations. And our job is to figure out whether or not these are functions just by looking at the equations. All right. Now the first one's kind of simple. Hopefully you spot that. Do you see how x and y are to the first power? So this is a line. Right? You could put it in y equals mx plus b form. You don't have to. It didn't ask you to do that. But as long as it can be put into y equals mx plus b form, then yes, it's a function. This is a diagonal line. Let me put it this way. Yes, a function. It's a diagonal line. When you see x and y both raised to the first power like that, that's a line. Right? Now, what about, or diagonal line, I should say. Now, what about letter B? Well, letter B's got a little bit of a different issue. That's x equals 2. That's a big fat no, right? Not a function, because this is a vertical line. Vertical lines are not functions. They would not pass the vertical line test. Any vertical line would hit this thing all over the place. So this is no good to us. Vertical lines are not functions. All right, now what about C? My answer to you is yes, C is a function. What would happen is, as a matter of fact, in case you want to know, it's a parabola. Right? So every x would only go to one y. So, pick any number you like for x, like 2. When you square it, you're going to get 4. It's not like you take 2, square it, and you get, I get 4 or I get 7. No, that's not how it works, right? 2 squared is equal to 4. 3 squared is equal to 9, and so on. Every x value you would pick, you could square it and you're going to get a different number, right? All right, so C is definitely a function, and I'm going to tell you right now that D is not. Now the problem with D And I can prove it to you a couple different ways. But the big issue with D is the whole y squared business. Let me give you an example. Oops. Okay. If I had x, actually, let me do it this way. X and y. There we go. Let me just bear with me for a second. Suppose y was 3, right? No problem. So you say, okay, y is 3. If I square it, my x value will be 9. Okay, so far you're not seeing the problem. I don't disagree. But then suppose I took negative 3. If I square it, I'm also going to get 9. See the problem? I have one x value of 9 going to two different y values, 3 and negative 3. That's not good, right? That is not a function, not by any stretch of the imagination. And I know you're thinking, well, Alana, how come that one works that way, but this other one over here on the right, how come that wasn't the problem there? Well, that's because for that one, the issue is the x, right? X is the thing that's squared, right? So I could take x is 2, I would get 4. I could take 3 if you like it, and I could get 9. And I could take negative 3, and I would also get 9. That's a negative, sorry. Right? I have two different x's going to two different, or well, the same y, right? But I don't have a repeat in my x. See that? 3, the number 3, only goes to 9 because x is squared, right? The issue is over here on the other one, it's the y that's squared, and that is problematic, right? We don't like the y being squared like that. That's not good for us. Okay, so we need to make a note to ourselves. Anytime, let's see, y, ooh, goodness, y to an even power is never a function. Never, never, never. It's never a function in terms of x, which is what we're interested in this class. Right? There are other ways around that, but there we go. I got it all to fit on the same page. Okay, so y to an even power is never, 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 never a function of x. Right? X to an even power, I don't really care. But y to an even power, any even power, because they'll all have the same problem of when you square them, or if you take them to the 4th power, whatever, it'll still turn it positive. So because you're squaring, it turns everything positive. And that means that if y is to an even power, raised to an even power, never, 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 never going to be a function. All right, let's go move on to this. This is what I was saying before about there's 4 ways to interpret things. You can do it algebraically, that's with like x's and y's. Numerically, that's a table. Graphically, that's a graph. And then with words. Okay, so is the relation y equals 1/2 x minus 3 a function? Yes, right? All diagonal lines are functions, so all right. Oops, I spelled functions wrong, but that's okay. All right, then it said describe the input-output pairs in a table, i.e. that's numerically. Okay, so they started you off with the algebra right here. So there's the algebra. And then now they're moving you on to the table. So we could make a table full of points. So we need x's and y's. Okay. Now, what are some points we could pick? Well, you can kind of use intelligent points here. I would highly recommend it. But you can also use your calculator to kind of help you out. I mean, if you're a little bit stuck and you're thinking, oh, what would be smart? So you know that 0 is always kind of a good idea. Matter of fact, everybody should know it's 0, -3 just by looking at it, because that's what your y-intercept is, -3. But 1 would not necessarily be the best pick because you're going to have to graph this thing and 1's going to come up with a decimal. So what might be wiser is to, well, I'll show it to you. Use your calculator to kind of help yourself. 1/2 x minus 3. And you go to the table, and instead of taking 1, because 1 works out to be this decimal, why don't we take 2? 2 works into -2. 4 works into -1, right? So let's see, 2 went to -2, 4 goes to -1, and then negative 2 must go to negative 4, and whoopsie, negative 4 goes to negative 5. Let me double check those. Yep. Now how am I doing that? Well, every time my x was going up by 2, see that? 2, 2, 2, 2. My y was going up by 1, because that's what my slope is, right? Change in y is 1, change in x is 2. They're both positive, so they're both going up, right? All right, so now I'm going to have to use a graph to graph these points. So describe those 5 input-output pairs by making a graph. I could do that, and not only that, I could actually make a graph of the line, which is this relation. So I'm going to do that. Hold on one second. There it is, like magic. So I graphed each of those points, negative 4, negative 5, negative 2, negative 4, and so on. I could have grabbed more, right? There's lots more to be had. And then I just drew the line that connected it. And that's using a graph to describe what's going on, right? So I've done it numerically, graphically, and then I had the equation to begin with, so that's the algebra. Now what's happening in words? Okay, so this is kind of not super useful at this point, but what we're going to say is we multiply the input by 1/2 and then subtract 3.